Hello, I'm Muhammad Islam from Swinburne University of Technology, Melbourne, Australia. In this presentation, I will discuss differential privacy-based permission blockchain for private data sharing in industrial IoT. Other co-authors of this work are Mubashir, Husain, Rehmani, and Jinjun, Chen. First, I will start with introduction, in which I will give some background. Then, I will give overview of existing methods and research questions. Followed by this, I will discuss proposed work and system model, working of the proposed model. Then I will discuss performance evaluation and results. Finally, I will conclude the presentation and discuss future work. Background. Industrial Internet of Things is a massive network of devices such as robots, sensors, machines, and controllers. It has various applications, for example, real-time monitoring in healthcare and supply chain, reduced overall costs, and predictive maintenance. Blockchain is an emerging technology, which is a distributed ledger in which data is recorded through cryptographically connected blocks. It has various features such as security, privacy, transparency, and tamper-proof records. It can be divided into permissionless and permissioned blockchain. In permissionless blockchain, each participant is allowed to see the contents of the blocks, which results in several privacy and security issues. On the other hand side, permission blockchain limits the visibility of contents of blocks to certain participants of the network. Therefore, we selected permissioned blockchain. More specifically, we adopted Hyperledger Fabric in this work. Blockchain is integrated into industrial IoT. The motivation for this is to enable tracking, transparency, and verification at various stages. Furthermore, the data is shared between the participants of the network, such as manufacturer, distributor, and retailer, to incentivize each other. Similarly, differential privacy is a de facto standard for privacy definition. Mathematically, equation 1 represents the differential privacy, in which the epsilon represents the privacy budget. Similarly, differential privacy is implemented through Laplace mechanism. Equation 2 represents Laplace distribution, in which lambda represents the Laplace scale, mu represents the mean of the distribution, and x is a random number. It hides individual record in a set of data records. Furthermore, the addition or removal of a single record has negligible effect on the final output. Overview of existing methods. Most of the existing methods use encryption and built-in security and privacy mechanism for private data sharing. Similarly, they use pseudonymous communication, unlinkability of transactions, and mixing techniques. However, this results into several disadvantages. For example, black market activities, high resource consumption, and less utility of industrial data. On the other hand side, Hyperledger Fabric has some private data sharing mechanisms. For example, multi-channels, private data collection, hashing, and transient field of transaction. And the fourth one is queuing of the ledger. In this work, we will be focusing on queuing of the ledger. The problem in query mechanism is that query is evaluated on the actual data of the ledger, which gives rise to privacy issues such as reveal of business secrets, discounts, offers, and shopping activities. Based on this, we raised two research questions. So the first one is how to share private data in a blockchain-based IoT environment in order to incentivize the network participants in a privacy-preserving manner. The second question is how to integrate differential privacy into the chain code of Hyperledger Fabric in order to hide an individual record in the data. To answer this, we have proposed differential privacy-based permission blockchain using Hyperledger Fabric for private data sharing in IoT, which is called DHIoT. The elements or the components of the system model are client applications, endorsing pairs, orderer pairs, and applications. We have considered a supply chain scenario which consists of manufacturer, retailer, and distributor. The participants can share and access data of each other. In the adversary model, competitors in the supply chain network try to reveal secret business plans of its rivals and shopping activities of customers through linking attacks. The working of the proposed system model can be divided into 4 steps. In the first step, the client application sends transaction proposal to endorsing pairs. In the second step, the query transaction is evaluated and Laplace noise is added to the actual value through the proposed algorithm, which is discussed in the next slide. So here, the manufacturer sends a transaction which consists of a query to the retailer. The chain code of the retailer evaluates the transaction or the query on the ledger, and then a Laplace noise is added to perturb it. After this, it is returned to the manufacturer. In this way, the privacy is preserved for the retailer. In the third step, the ordering node collects all the transactions from the client applications and sequences them into blocks. In the final step, the endorsing pairs validate the transaction in the blocks. If they are valid, then they are committed and appended to the chain. This is our proposed algorithm. In the proposed algorithm, each transaction consists of a query, Fi. Then a random noise is generated through the Laplace mechanism using the Laplacian function. The random noise depends on the initialized parameters for differential privacy. The while loop executes according to the number of transactions. The random noise is added to the query response and returned to the requester. The complexity of the algorithm is O of n, which means that it increases linearly with the number of transactions. Evaluation. We configured the Hyperledger Fabric network with 2 organizations having 1 pair per organization with a couch database. A single channel called myChannel is configured between the pairs. We also configured 2 rounds. In the first round, we send 500 transactions to initialize the ledger, and in the second round, we send 755 random query transactions. The differential privacy parameters are set up according to these values. We evaluated 4 parameters, which includes privacy preservation, relative error, throughput, and latency. We also compared our proposed DHI IoT with the existing chain code of Hyperledger Fabric. In this graph, the privacy preservation results are presented. On the left-hand side, the result for epsilon 0.5 is presented. The x-axis represents query transactions, while the y-axis represents the number of items purchased for both Hyperledger Fabric chain code and our proposed privacy-preserving chain code, which is known as DHI IoT. The query responses are a little bit different from the existing chain code because of the perturbation. Furthermore, it can be seen that high privacy preservation is achieved, which is equivalent to epsilon 0.5 in the DHI IoT, while at the same time, acceptable accurate results are generated, which is equal to 96.15%. On the other hand side, the existing chain code of Hyperledger Fabric doesn't use any perturbation. Similarly, on the right hand side, the result for epsilon 1 is presented. It can be seen that increasing the epsilon increases the accuracy of the data in the DHI IoT. In this graph, the relative error and accuracy are evaluated. On the x-axis, privacy budget is varied from 0.5 to 2.5. The y-axis represents the average relative error on the left side, and on the right side, accuracy is represented. It can be seen that increasing the privacy budget decreases the relative error. At the same time, increasing the privacy budget results in increasing the accuracy of the data. For higher values of privacy budget, the accuracy of the data is very close to 100%. Similarly, The relative error for Hyperledger Fabric is 0 for all values of privacy budget. The reason is that the existing Hyperledger Fabric chain code doesn't use any perturbation. In this graph, the throughput of the transactions are evaluated. On the left-hand side, the result for write transaction is presented. The x-axis represents the variation of input transactions, while the y-axis represents throughput. It can be seen that the throughput increases with the increase in input transactions. The reason is that more input transactions will result more output transactions and hence throughput. Similarly, on the right-hand side, throughput for query transactions is represented. In the same fashion, the throughput increases with the increase in input transactions. In this graph, the results for latency are presented. On the left-hand side, the result for write transaction is presented. It can be seen that the latency decreases until 40 transactions per second, while beyond this point, the latency shows an increase. The reason is that at this point, the Hyperledger Fabric network reached its maximum capacity of transactions processing. And beyond this point, increase in the input transaction rate also increases the latency. Similarly, on the right-hand side, the latency for query transactions is presented. In the same fashion, it also shows an increase in the latency from the start. Furthermore, a latency of almost 14 seconds is achieved for input transaction rate of 50 transactions per second. Conclusion and future work. We presented a differential privacy-based permission blockchain for private data sharing in industrial IoT. We integrated differential privacy into the chain code of Hyperledger Fabric. We presented an algorithm for adding Laplace noise into the query response. We also evaluated our proposed Hyperledger Fabric network for privacy preservation, accuracy, throughput, and latency. It was found that the proposed work achieves high privacy preservation with sufficient accuracy of 96.15% in the data in comparison to the existing setup of chain code of Hyperledger Fabric with no privacy guarantee. In the future, we will perform simulations on other blockchain platforms and simulate composition attack along with the linking attack. Similarly, we will integrate differential privacy into the consensus mechanism in order to hide the transaction and the transaction miner and make it anonymous. Thank you.